Check this out. That, my friends, is the Doppler effect. Did you notice how the pitch changed after they passed this? The pitch change is covered by what we would call the Doppler effect. When I learned this, immediately I asked myself, does the Doppler effect change when the source of the sound is orbiting the observer? To answer this, I went to my closest friend and associate, Michael Kim. All right, the Doppler effect. Let's take this source that is actively emitting sound. And let's pretend this is me talking, and this is you filming that. And let's say instead of a stationary source, let's say this source was moving at a certain speed. And so basically it would look like this. This is the sound wave, and this source is now on the edge of the sound wave. So basically, once the source emits another pressure wave, it's going to look something like this. It's going to look like that. And if this source was going around like 340 meters per second, and since the speed of sound is 343 meters per second, if each pressure wave was released 1 second apart, then this would be equal to this distance would be around 3 meters. And then this distance would be 683 meters. Wow, that's crazy. Well, it's because I created a situation that made the Doppler effect easier to explain. The Doppler effect is all around us. Crazy, I know. And it only gets crazier. The Doppler effect also applies to light. Just as the Doppler effect changes pitch in sound waves, it changes the frequency of the light relative to observers. Higher frequencies of light mean bluer light, and lower frequencies of light mean redder light. This effect is known as redshifting because red-shifted light sources are the most common as the universe is expanding. And now it's time to learn what's actually going on mathematically behind the scenes. All right, thanks, Michael. So, to find the frequency of the observed sound, you need to have the velocity of wave propagation plus the velocity of the observer, all divided by the velocity of the speed of wave propagation plus the velocity of the source. And all that, once multiplied by our source frequency, will give us the source of the frequency of the observed. And thank you, Maddie, for letting me use your whiteboard. Okay, now here's some math explaining that little experiment you just saw. Let's erase this. Okay, so if the source is staying a constant relative distance away from the a constant relative distance away from the observer, then the waves won't bunch up like Professor Michael explained earlier. And